And here we go. Good morning. Good morning. Hi, everyone. 안녕하세요, 여러분. Great, great. So we're currently discussing online algorithms and the analysis of online algorithms. And nice online problem we've discussed is the ski rental problem, where the program or the users to decide on a daily basis whether to rent a pair of skis for another day of skiing or to buy, to make the investment of a pair of skis so that there's no need to spend money on renting once the purchase has been made, but the purchase is expensive. So you want to make sure that your purchase is worthwhile, but you cannot tell that in advance because it depends on how long the season, the skiing season lasts, right? So this is an example where the algorithm is not presented the entire input in advance. The entire input in this case would be the entire sequence of weather information, but this is not available to the algorithm advance before starting to process. So the algorithm must start making decisions based on incomplete data. Um, and in this, therefore, it cannot make the optimal decision always. So when we analyze such online algorithms, we compare their performance with the performance of an optimal, omniscient offline algorithm, which is supposed to know miraculously all the data in advance. So even if this offline algorithm cannot perform well, then also our online algorithm is not expected to perform much, to perform well. So that's kind of a relative measure of performance. Compare the online algorithm to an offline algorithm. Let me again emphasize that point. So if for some reason even an omniscient algorithm cannot give a good performance, then we don't expect the online algorithm to perform well either. So if the online algorithm, even in these bad cases, comes within a certain range of the optimal offline algorithm, then we say that our online algorithm is competitive. So that's not an absolute measure of performance, but relative to an omniscient optimal offline algorithm. And we've discussed a simple strategy for the online ski rental problem, namely the break-even algorithm. The break-even algorithm um, rents for D minus 1 days and then makes the purchase. And the idea, the intuition is after having spent D minus $1, where when the choice comes to spend the $D on rental, and that's kind of, you see, the money paid on rental is kind of lost, right? Then once this money that has been spent becomes equal to the money, to the cost of an actual purchase, so that something that actually retains value, namely buying a pair of skis, at this moment, when this break-even point has been arrived, has been achieved, then the algorithm um, changes its strategy, moves on to make the purchase, right? So that's generally speaking in business environments a common strategy. Uh, break even when the fixed cost and the anyway, I'm not an economist. So that's the idea of the break-even algorithm. So, and we've analyzed that the break-even algorithm, um, if the break-even is not attained, then it makes or it's expensive or as long as the season lasts. So if the season is shorter than D days, then the break-even algorithm will never move on, never proceed to make the purchase, but it will keep on renting. So if the length of the season, which we will denote with L, if that length is less or equal to D, the cost of the purchase, then the break-even algorithm will spend L dollars. Whereas if the season is longer, or at least as long as the oh, there's a strict inequality missing. Anyway, so if the season is at least as long as D, then the break-even algorithm makes a purchase. In this case, it has spent D minus $1 on rental and another D dollars on the purchase. And then it doesn't matter how much longer the season lasts, because then the money has already been spent and no further decisions are to be made. And we've compared this with the cost of an omniscient offline algorithm, which miraculously knows that the season is going to last for L days. And then, based on that knowledge, can decide if L is less than D, the cost of a purchase, then it is more reasonable, then it is less expensive to keep on renting. Whereas if the season is longer, or at least as long as D, then it can make a purchase and on the very first day, never rent. So the offline algorithm either always rents or never rents, based on knowing in advance uh, how long the season is going to last. And then we have compared these two algorithms, we have compared their cost, right? In order to determine the competitive ratio. How well does the online algorithm perform in comparison to the optimal offline algorithm? And we have seen by considering the several cases that this ratio is always less or equal to 2 minus 1 over D, and in particular it's always strictly less than 2. There were several cases, but it's really easy math, so I'm going to skip this proof. And the conclusion is that the break-even algorithm is not just a heuristic, as many are in business situations, but we've turned this into a rigorous algorithm by analyzing and proving that it is 2 minus 1 over D competitive, and in particular it's too competitive. It will never perform worse than twice as bad as an optimal offline algorithm. So if the situation is such that an offline algorithm performs well, then also our break-even algorithm will perform well. And if the input is such that even an offline algorithm cannot perform well, then there's no much expectation for a break-even algorithm either. And then we've proceeded with our virtues of computer science, namely we've shown that this competitive ratio is actually optimal. Namely, we've shown that any online algorithm, which is any algorithm which is not omniscient, which cannot tell in advance how long the season will last, will have competitive ratio at least 2 minus 1 over D. And to this end, we've considered an arbitrary online algorithm A, and we've executed it as a thought experiment. We've executed it twice. First, we've executed it on a season which to the algorithm seems to be infinite. So every morning, we've told the algorithm, today the season is still going on, you can still go on skiing. And if the algorithm will never resort to buying in this case, then the algorithm cannot get a bounded competitive ratio anyway, because then the cost of this algorithm will go to infinity as the length of the season goes to infinity, which is much, much larger than the cost D of a purchase. So therefore, this case is kind of the uninteresting case. Any reasonable online algorithm will eventually switch to making a purchase. And with in our thought experiment, in our simulation of this algorithm, we've recorded this and have counted the number of days it rents before making a purchase, and we've denoted that number with X. And based on that X, we have created an input where the online algorithm A performs bad. Namely, we've created a situation where the season lasts for X plus 1 days. So remember, X denotes the number of days that the online algorithm rents. And now we've created a season which lasts for X days and 1 day further. So that put differently, on the last day of the season, we design the season in such a way that the hypothetical or arbitrary online algorithm A uh, makes a purchase, and just after having made a purchase, we kind of interrupt, terminate the season. And we can do that because our hypothetical online algorithm that we're analyzing is an deterministic algorithm. That's crucial, right? So that's crucial because it means once we rerun the algorithm on our season, the length of the season we've created from first running the algorithm, then the algorithm will perform in the same way again, deterministic algorithm, right? And I mean, what will it do again? It will again keep renting for X days, because up to the first X days, our new situation, our new season looks the same to the online algorithm as in our first execution, where the season was kind of infinite. And let me emphasize that it's crucial that this is a deterministic algorithm. And only on the first X plus first day, our newly constructed scenario or new season is terminated and therefore differs from what the online algorithm does. But then it's kind of too late. It already has made a purchase, and therefore it already has spent a total of X dollars for rental and the D dollars on the X plus first day for the purchase. So this is kind of a worst case for this online algorithm, and we have constructed a season which constitutes this worst case after we have analyzed the algorithm and determined its worst case. And now let's compare that to the omniscient offline algorithm, which somehow knows how long we make the season last. So it knows that the season lasts for X plus 1 days. So depending on whether X plus 1 is less or greater than D, it will either keep renting or make a purchase on the very first day. In either way, in either case, the cost incurred by the optimal offline algorithm is the minimum of the two quantities. If the season is shorter than X plus 1 days, then it will buy on the very first day D. If the season is uh, longer than X plus 1 days, uh, no, the other way. If the season is uh, longer than X plus 1 days, then it will make a purchase on the very first day and thus incur cost D. If the season is shorter than X plus 1 days, then it will always keep renting and therefore incur cost X plus 1. And but that's only available, that information is only available to the optimal offline algorithm. And then we've estimated the ratio between the two quantities, right? That's a competitive ratio of our arbitrary uh, online algorithm. And we've determined, again, by considering two cases, that this ratio is always greater or equal to 2 minus 1 over d. That means that any online algorithm, and let me say it again, any deterministic online algorithm for the ski rental online problem cannot do better than competitive ratio 2 minus 1 over d, cannot do better than the break-even algorithm which attains this competitive ratio. Therefore, the break-even algorithm is indeed an optimal online algorithm for the ski rental problem. And in this second part of the proof, we proved optimality, where we proved that any deterministic online algorithm has competitive ratio at least 2 minus 1 over d. Observe that we have deliberately constructed such a worst case scenario, and this is called an adversary argument. we are the adversary to the algorithm. We create a worst case situation after first analyzing the algorithm. So this is a important technical term, a popular way of proving optimality of online algorithms. And yes, I've already emphasized that all of this applies only to deterministic algorithms. And I emphasize this because at the very last slide of this chapter 6, we will also consider a randomized algorithm for the ski rental online problem. But let's stay tuned for that. Okay, so much about recapitulation. Let's now move on to consider another popular online problem, namely the paging problem. So in paging, we have small k pages with fast memory, and they are used to accelerate access to a large but slow memory, large having capital K pages. So that imagine that to be a hard disk, for instance. And at any stage, the fast cache contains copies of some of the pages on the disk. So in this example, the pages number 19, 5, 8, 2, 11, and 7 are stored in the cache. And when a new page is requested for read or write, then the caching algorithm must first uh, expunge a page from the cache. That means it must first write the content of the page from the cache to the disk, and then read the content of the new page into the test tree in the slot, which has thus become available. So, for instance, if this algorithm wants the user algorithm wants to access page number 8, then uh, it can do that very quickly because 8 is already in the cache. Whereas if the user algorithm now wants to access page number 1, this is not in the cache. Now our paging algorithm must make a decision which page to expunge to make room for the new page number 1. And this is a, a difficult decision for our online paging algorithm because it does not know which page the user program will access next, right? So, for instance, suppose we decide to expunge page number 19 in order to make room for page number 1. And in the next step, the user algorithm wants to access page number 19. Then we're kind of bummed, right? Then we would have better expunged page number 5 to make room for page number 1 and keep page number 19 in the online cache for the next access. But maybe the user algorithm in the next step wants to access page number 5 instead of page number 19, then we better had kept page number 5. So in retrospective, knowing what the user program will access next, that's exactly the available, that information is available to our hypothetical optimal offline algorithm. But as an online algorithm, we cannot predict in advance which page the user program will access next. So we have to design an algorithm that performs well even under this situation, but well, always performs well in comparison to the optimal offline algorithm, not necessarily absolutely. And we will emphasize that important point when we discuss some examples in a few minutes. Right. This is the situation I've just described, where our online algorithm has decided to expunge page number 5 to make room for page number 1, which is thus read from the cache, and page number 5 before has been stored on back to the hard disk. So more formally, consider sequence of accesses to different pages, the sequence of accesses performed by the user program. So we the sequence exists, but our online algorithm does not know that sequence in its entirety. It only gets to know one entry after the other. So for any such sequence of accesses, the goal of an online algorithm is to minimize the number of cache misses, that is to minimize the number of loads and evictions of pages from and to the slow hard disk. And popular online algorithms for caching are least recently used, least frequently used, first in, first out, and the page with the minimum number uh, in the cache is expunged. And in this lecture, in this chapter, we will analyze the first two, least recently used and least frequently used. So let's recall the least recently used algorithm. So the algorithm is informally described as follows. Whenever the user program accesses a new page, which creates, suppose this creates a page fault, then our LRU algorithm will evict from its cache the page that has been least recently used. Put differently, our caching algorithm maintains with each entry in its cache timestamp when this page has been accessed, and whenever the page is accessed, this timestamp is updated, and otherwise it keeps lagging behind the actual system clock. So in this way, the caching algorithm can determine which page has been least recently used by running through the cache and looking at the timestamps, looking for the oldest timestamp. That's a timestamp of the page that has been least recently used. So this is kind of our time axis. This is at each tick corresponds to an access of the user program to some page in the cache, and sometimes there occurs a cache miss, a fault. This is indicated with symbol like this. So here a page is accessed which is not currently in the cache. So this creates a cache fault, cache miss, and requires our algorithm, our online algorithm, to expunge and reload this cache. So expunge to choose which page to evict, and then reload this new page. And in our online analysis, we want to compare the performance of this algorithm least recently used to an optimal offline algorithm, which miraculously knows the sequence of accesses A of the user program. Um, we want to compare and bound the ratio of the two algorithms incurred costs, the number of page faults occurred by the least recently used algorithm divided by the number of page faults incurred by an optimal omniscient online offline algorithm. And we suppose that both start with the same initial cache content, or maybe that initially the cache is empty. And now we perform an analysis, and the analysis performs the following mathematical trick. So let's say this is another cache fault, and what we do in our mathematical analysis, we divide the total number n of accesses performed by the user program, the total number n of ticks here, into rounds. With a property that within each round, the least recently used algorithm incurs precisely k faults. So we introduce timestamps, kind of, t, small t, such that in each round, which starts just after t minus 1, so that's when there's a open interval here. So the round starts just after time frame t minus 1 and lasts until and including time step t. And we choose the time steps in such a way that in each such round, there are precisely k faults, precisely k faults, and we will see in a minute for the purpose why this is a great choice for our analysis. How can how can we make sure that such a partition into rounds exists? That's of course an important question, and we can create such a partition into rounds as follows. We start backwards. We look at the very last um, um, right at the last time step, and then we look backwards, right, until look when a page fault occurs, and then another page fault, and so on until we have collected k page faults, starting looking back from behind until we've collected precisely k page faults. This is where the last round ends. And then we repeat the same process again from this round, start looking backwards to the front until we've collected precisely k page faults, and so on. This gives rise to this partition of the entire execution time of the user program into these rounds, such that each round has precisely k faults, except for the very first round, because it could happen that the total number of the page faults is not a multiple of k, right? Then we cannot uh, maintain the same property for the very first round. All rounds except for the very first round contain precisely k faults, but the first round is supposed to contain any number of faults from 1 up to, but less strictly, yes, from 1 up to k. 1 up to k, but not 0. That should be a closed bracket. Okay, so this is a partition of the hypothetical execution of an arbitrary user program and how our least recently used algorithm performs in that case. And we're going to compare that to the performance of an optimal offline algorithm. And for the purpose of this comparison, we're going to consider each round separately, and we're going to prove that in each round, the optimal offline algorithm incurs at least one page fault. So let me repeat that. We've constructed the rounds in such a way that in each round, our least recently used algorithm incurs precisely k faults, and we will show that in each such round, an optimal offline algorithm incurs at least one page fault, so that the total number of page faults incurred by our online algorithm is at most k times the number of page faults incurred by any optimal offline algorithm. Does that make sense? So let's pause here for a second for you to digest that statement. Let me say it again after the pause. So Robert asked, what is a round? So consider an arbitrary user program that an execution of a user program that accesses pages, and our least recently used algorithm maintains the cache of size small k for that between the user program and the actual slow hard disk. And the user program, let's say, makes a total number n of accesses to various memory pages, and we want to analyze how well does our least recently used algorithm perform. And for that purpose, we divide the number, the sequence of page accesses of the user program into rounds, into phases. That's for the purpose of our analysis. And we want to subdivide this sequence into, you see this here, this is one round, this is one round, this is one round. And we want to make the rounds have length chosen carefully such that in each round our least recently used algorithm incurs precisely k faults for the user program. Okay, and that's the purpose of a round. A round is kind of a time interval, and the time intervals are not of equal length in terms of time, execution time, nor of equal length in terms of how many pages are accessed, but they are of equal length in the sense that in each time interval, the same number, exactly k page faults occur. So in our analysis, we consider such partition of the entire execution time into rounds with this property. And we have argued that such a partition always exists, except for the very first round, because the very first round, if the total number of page faults is not a multiple of k, then we cannot partition the entire time frame into intervals such that each interval incurs precisely k page faults, right? So if that's possible, then that means that the total number of page faults is an integer multiple of k. But if it's not, then this is not feasible. So we will need to treat the very first round separately. The very first round may incur any number from 1 to k of page faults. Yes, Robert is asking, why do we choose k faults in each round? That's a good question, but that will become apparent in just a minute when we now start comparing the performance, the cost incurred by least recently used, compare that with the cost incurred of an optimal offline algorithm. Namely, we're going to argue that in each round, an optimal offline algorithm incurs at least one page fault. So least recently used LRU incurs k page faults by construction in each interval, and an optimal offline algorithm we will prove incurs at least one fault, so that the total number of faults of least recently used is at most k times the number of faults incurred by an optimal offline algorithm. Does that make sense? So in each round, LRU incurs k faults. We will prove that in each round, the optimal offline algorithm incurs at least one fault, so that the number of faults in each interval of LRU is at most k times the number of faults of the optimal offline algorithm, and therefore also the total number of faults of LRU is at most k times the total number of faults of the optimal offline algorithm, and that will conclude our proof of the theorem that LRU has competitive ratio k. It will not perform more than k times worse than an optimal omniscient offline algorithm. So, right, that's our goal, to prove that in each such round, even an optimal offline algorithm incurs at least one fault. And we're going to prove that by considering three possible cases. But before moving to the three cases, let's first treat the very first interval separately, where we don't know how many page faults it occurs. This is the exceptional interval. And so the claim is that even in this first exceptional round, an optimal offline algorithm will incur at least one page fault. And the reason is that we suppose that both LRU and the offline algorithm begin with the same initial cache contents, so that when LRU incurs the first page miss in the first interval, then also the optimal offline algorithm will incur a page fault, because up to this point, none of them had any choice of which page to evict or keep, right? So up to here, all pages can be served by both algorithms from the cache, and when the first page fault is suffered by LRU, then also any online algorithm will suffer a page fault. And only from there on, the two algorithms can possibly start to differ. So the baseline is that even in the first interval, where the LRU occurs a number of faults between 1 and k, then even in this interval, the optimal offline algorithm will also incur at least one page fault. So with that, the ratio is at most k in the first interval. And now we proceed to similarly consider all the other intervals, the non-exceptional intervals, where we do know that in each such interval, the number of page faults suffered by LRU is precisely k. And to this we consider three different cases. And the first case is deliberately the easiest case, namely, suppose that the k page faults, let's suppose these symbols here represent the pages that are accessed by the user program but cannot be served by LRU because they're not present in the cache. Let's suppose these are the page faults, right? And in this example, observe that this page fault, this page is accessed but not present. Then the cache algorithm loads that page into memory and evicts another page. Here's another page being accessed, which is not present, therefore has to be loaded into the cache, and another page has to be evicted. Same here, but this is the same page in this example that has been caused a page fault here already, right? So let's first record if this happens, if the same page incurs a page fault again, then that means that between these two pages, the user program must have accessed at least k other pages, right? Let's say that again. If between these two identical pages, if both of them incur a page fault, then the user program must have accessed at least k distinct pages, because otherwise there would not have been any need for a paging algorithm to evict this page. Otherwise, it would have kept this page in the cache until this time and would not have caused another page fault here. Let me say that again. So here's a page fault, here's a page fault. The algorithm will try, any reasonable algorithm will try to keep that page in the cache as long as possible. So, but apparently it could not keep that in the cache because in our scenario, this is another page fault. So that means that in between, at least k other pages must have been accessed by the user program. That's the only way that the same page can incur another page fault. And that means that the user program has accessed actually k plus 1 different pages, k different pages here in between, and this here is the k plus first page. So that means that's our conclusion for this case. In this case, the user program within this phase, more precisely within this subinterval of the phase, has accessed k plus 1 pages, and even the best offline algorithm cannot maintain k plus 1 pages in a cache of size k. So that means that even in this case, the optimal offline algorithm will have had to suffer at least one page miss because the cache has only size k. Let me say it again. In this case, we're currently considering where the same page incurs a page miss twice in the current phase, in the current round. Then that means that the user program in that round must have accessed at least k plus 1 different pages. And that means that even the optimal omniscient offline algorithm must have suffered at least one page miss. It cannot keep k plus 1 pages in a cache of size k. So that's the first case we've thus covered in our proof, that in each round, even an optimal omniscient offline algorithm will incur at least one page miss. So what pair cases now remain? The case where all the page faults incurred in this round are pairwise distinct, right? That's the opposite from the same page causing a page fault twice. The opposite means that all the page faults refer to distinct pages. So, and since the number of page faults is k, that's why we choose the rounds, how we choose the rounds, so that the number of page faults is precisely k. That means there are precisely k different pages causing k different page faults, and therefore k different pages being accessed by the user program. Now we're almost there at our claim that even the optimal offline algorithm will suffer a page fault in this scenario, but our cache has size k, so it could hypothetically indeed contain all these k different pages, and maybe only our online algorithm is doing a bad job in maintaining this, but the offline algorithm is not. But this is not the case for the following reason. Let's consider the last page accessed before the current phase starts. And let's suppose that the page accessed here is different, distinct from all these pages that incur page faults here. And we say it again, by construction of our rounds, we have k page faults here, and the case we're currently considering is the case where all these page faults refer to different pages, because the other case we've already covered. If they consider different pages, then there's k different pages being accessed by the user program. And now we consider another page, namely the page accessed just right before the current round, this one. If this page is different from all the k pages that incur page faults here, then again we have identified k plus 1 different pages accessed by the user program, so that also in this case even an optimal offline algorithm will suffer at least one page miss. So let me say it again, the case we're currently considering is that the number that all the page faults refer to different pages, and there's another different page being accessed right before the current phase. That makes a total number of k plus 1 different pages, and there on these k plus 1 pages, even an optimal offline algorithm will incur at least one page miss for a cache of size k. What remains to consider is the final case, namely where this page accessed here agrees with one of the k pairwise distinct page misses, right? So that's the final case. At least one of all the page misses here inside the phase refer to k pairwise different pages, but the page accessed right before the current round coincides with one of these pages that incur page miss. But then we can apply the same argument again as we did here. If these two page faults are caused by accessing the same page, then in between there must have been k other pages accessed, making a total number of k plus 1 pages. And the same applies in this case. So to summarize, we've considered three different cases that are all possible cases for what could happen within such a round, for such a round to incur k page faults, precisely k page faults, and we've shown that in each of these three cases, even an optimal offline algorithm must incur page fault, because in each of the three cases we've identified k plus 1 different pages being accessed, and only k different pages fit into the cache. So since this applies to each of the rounds, that means whenever the least recently used algorithm incurs k faults in such a round, then that's at most k times the number of faults incurred by the optimal offline algorithm. And there was an exceptional round. That's the very first round, and we've covered that as well, where we argued that the first cache miss suffered by the least recently used algorithm is also a cache miss to be suffered by the optimal offline algorithm. Okay, so Sojin and Robert have asked me to explain the third case again, and I will happy to do that. Thanks for your questions. Okay, so let's recall the three cases because they kind of pedagogically built on each other. First cases when among the K page faults, one page occurs repeatedly, causing a fault, page fault, and again causing a page fault. And in this case, we've seen that between the K other pages being accessed, therefore resulting in a total number of K plus 1 distinct pages being accessed. The second case is where all these K page faults refer to K different pairwise distinct pages, but then we've also started looking at the page being accessed right before the current round. And if that page is different from the K pairwise different pages here, then again we have K plus 1 pages, and we're in business, we have covered the case. And the remaining, the third case you're asking about, is the case where all these K page faults refer to pairwise distinct pages, but the page accessed right before the current round refers to a page which coincides with one of the K distinct pages. But this is the same, basically the same case as our first case. We have 2 times a page fault occurred by the same page. Here, this is a page accessed, and here the same page, or let's say this page is the same as accessed here, right? So it's the same symbol. Here it occurs a page fault. That means the page must have been evicted somewhere in between. That means the user program must have accessed at least K other pages in between together with this page. That makes a K plus first page. So K plus 1 page cannot be maintained even by the optimal omniscient offline algorithm, so that even in this algorithm must incur at least 1 page fault in the third case. So that you're welcome. Thank you. Thanks for asking. Thanks for the opportunity to clarify. So that basically we have 4 cases covered. The first exceptional case is the first round, and for all other rounds we have considered 3 different cases, and we've made sure that all these 3 different cases cover all possibilities, and that in each of these 3 cases the optimal offline algorithm incurs at least 1 page fault, because in each of the 3 cases their user program accesses at least K plus 1 pages. Let me say it again in this different way. The rounds, we've created the rounds, we've constructed the rounds such that in each round LRU incurs precisely K point fault, and we have concluded that in each round the user program accesses at least K plus 1 different pages, and therefore in each case even an optimal offline algorithm must suffer at least 1 page fault. It cannot maintain K plus 1 pages in a cache of size K, and therefore the ratio of page faults in each round between optimal offline algorithm and LRU is at most K, and therefore the same also applies for the entire execution of the algorithm. So that concludes our competitive analysis of the least recently used paging strategy. We've proved that this is K competitive, which means, let me emphasize that again, it doesn't mean that the algorithm is efficient always, but it's only efficient in comparison to an optimal offline algorithm. You can easily imagine we will soon see a scenario where even the optimal offline algorithm cannot perform well because the user program just behaves so strangely that the cache cannot be really exploited. And then our competitive analysis also says that LRU also will perform badly, but of course it can never perform better and an optimal offline algorithm. So instead, a more fair way of comparing online algorithms is by comparing them, their performance in comparison, in relation to an optimal offline algorithm. And this is what we did. Okay. So yes, this is a conclusion. In each phase, the user program accesses at least k+1 pages. In each phase, any optimal offline algorithm therefore incurs at least one page fault, which is at most factor k less than the k page faults incurred by LRU, so that this is k competitive. Good, let's now move on to another paging strategy. We will discuss the optimality in a minute, but let's now move on to discuss another popular online paging strategy, least frequently used. So the least frequently used algorithm would like, how to say, instead of maintaining a timestamp with each cache page, when was the last time it was accessed, instead it will maintain a usage count. It will count how often the page has been accessed. And whenever a page has been accessed, then it would increment the user counter. Okay, that's the basis for the least frequently used strategy, and we're going to analyze the performance of this strategy again in comparison to an optimal offline algorithm, and it will turn out that this actually is a very bad online algorithm. It has no finite competitive ratio. We cannot say that it performs at most by a constant factor worse than an optimal offline algorithm. So in a sense, from a rigorous perspective, this is a bad algorithm. So, and in order to prove that, we're going to again construct a worst case, an adversarial sequence of accesses of a user program. We're playing this adversarial game of the optimality analysis of online algorithms. So we consider the following access sequence. Suppose k, small k, so cache size, and we consider the case where the main memory, the slow memory, has size at least k+1. Actually, it suffices to have size exactly k+1. Right, so if it has size exactly k, then there's no point in having a separate cache, right? Then we can just store the entire external memory into the cache. So the interesting case is really where the size of the external memory is strictly larger than the size of the cache. And even if it's only one larger, then least frequently used algorithm will turn out to behave very badly. So here's the counterexample, the adversarial, the worst case sequence of access. Let's suppose the user program accesses page number 2, 3, 4, k. Then again, it accesses page number 3, 2, 4, k, and so on. And it repeats that for a number of times, which we'll determine in a minute. And for now, we will just call this number m+1. Okay, so we say it again, we consider hypothetical user program, and we're going to consider it to have a access pattern to the memory, which will turn out to be very bad for least frequently used. Namely, this is the access pattern, access page number 2, 3, 4 up to k, then repeat access number 2, 3, 4 up to k, and so on. And repeat that m+1 times, and after that, switch to a very different access pattern. So the first pattern is very regular. The second access pattern is very regular, but differently. Namely, now the user program will switch back and forth between accessing the first and last page. Page number 1, page number k+1, page number 1, page number k+1, and so on. Okay, and we will repeat that for m times, not m+1, but m times. Okay, and we claim this is a very strange access pattern, but we kind of have constructed this admittedly artificially, and we'll show that this is a very bad case for least frequently used. But before looking at how least frequently used performs in that input, let's look at how an optimal offline algorithm would perform. How would you, if you were the caching strategy, how would you maintain your cache of size k if you knew in advance that this is how the user program will access memory? Well, the first n+1 phases here are easy. They all fit into the cache, right? So 2, 3, up to k, that's just k minus 1 pages, and they fit into the cache of size k. Now this next time, they are already in the cache, so there's no need for eviction or update, no page fault, neither here, all here, right? So once these pages have been loaded into the cache, then the user program will run smoothly. There will not be any cache fault. Now comes the second part of the access sequence. Here the user program will access alternatingly page 1. Page 1 will still fit into the cache, so no need to evict something. But now it accesses page number k+1. Remember, this is our hypothesis. But number k+1 is not inside of the cache, but the cache is already fully loaded, right? With pages 2 up to k and the newly loaded pages 1. So now we have to evict something, right? And which page do we evict to make room for the page number k+1? Well, as an optimal offline algorithm, we know that none of these pages will ever be accessed again. As you see here from the pattern, we can predict, we know that it's only alternatingly between 1 and k+1. So any of the apart phases can safely be evicted to make room so that the result of the access sequence can again be performed without having any further page fault. So that on this input, an optimal offline algorithm, which knows the whole input in advance, could get away with, let's say, k+1 cache misses here to first load the cache, and that's it. Independent of m, independent of how often we repeat this or this, an optimal offline algorithm will have only k+1 cache misses, and that's also, of course, the best one can do, because at the end the algorithm user program does access k+1 different pages, so k+1 different accesses. And now let's compare that behavior of the optimal offline algorithm to how our least frequently used algorithm behaves on this particular input. So again, least frequently used algorithm on the first part will do very well. Will only, once the first pages have been loaded, from there on they will not incur any further page faults up to here, right? But then the trouble starts, because well, page number 1 is still easy. It's still a free slot in the cache, but when evicting page number k, when accessing page number k+1, now which page would the optimal offline algorithm evict? Any of these pages, right? Because it knows they will never be accessed again. However, least frequently used strategy will evict the page that has least frequently been used so far. And this is page number 1. Page number 1 has been used only once, whereas all other pages in the cache have been accessed n+1 times, right? Which is more. So the least frequently used algorithm, when the user program requests this page, it will evict page number 1. But right after that, the user program wants to access page number 1, which has just been evicted. So another page fault occurs. Least frequently used strategy will need to evict a page. Which page will it evict? Well, page number k+1, because this is a page that has been least frequently used, has been used only once so far, as opposed to all the other pages currently in the cache, which have been used k+1, n+1 times. So another page fault here, and another page fault here, and so on, so that LFU strategy starting from here, will keep incurring page faults in every single access. And of course, as M grows, this will grow unboundedly, so that in comparison to the optimal offline algorithm, which only has k plus 1 cache faults regardless of M, the LFU strategy has M page faults here, and as M grows asymptotically, this means an unbounded competitive ratio, so that this is a bad algorithm from the perspective of online algorithms. Okay. We basically create a specific sequence of inputs so that uh, well, not any online algorithm fails, but the one we're currently considering. In order, our theorem says LFU algorithm has unbounded competitive ratio. In order to prove that, we create indeed a specific sequence. So we're the adversary where LFU performs bad, but the optimal offline algorithm can still perform good, so that in comparison also LFU is bad. It doesn't suffice for LFU to just behave bad absolutely, but in order to prove unbounded competitive ratio, we must prove that it is behaves badly in comparison to an optimal offline algorithm. And we construct such an input sequence. Like we, in CS300, you probably constructed an input sequence where quicksort behaved badly, where quicksort had quadratic running time, like maybe an already sorted sequence was such a bad input. And here, this is a bad input for LFU in comparison to the optimal offline algorithm. And we'll see such an example constructing a bad input sequence again on the next slide, where we consider the question of optimality on online paging. So now we've seen and analyzed two algorithms for online paging. LFU is out of the discussion. It has unbounded competitive ratio, but LRU, least recently used, seems to be a good choice. It is K competitive, and this raises the question whether there is a better online algorithm which is less, whose competitive ratio is less than K, strictly less, right? That's our usual question in all kinds of algorithm design. We design an algorithm, we analyze it, and then we ask whether there's a more efficient algorithm. And if there is, then we should design and analyze it, or we should prove that there isn't. Then we've already found the optimal algorithm. So the question we discuss in this slide is LRU optimal on online algorithm? And this is exactly what we're going to prove. We're going to prove that every deterministic online algorithm for the paging problem has competitive ratio at least K. So LRU attains that and therefore is optimal. And we do that again by constructing an adversarial sequence, a bad sequence, but this time the construction is more involved than on the previous slide. It again involves simulating the algorithm on a hypothetical input. That's also what we did when we constructed a bad sequence of weather events for the online ski rental problem. But here the input sequence is of course more complicated. It's an access sequence, not just a sequence of good and bad weather. So what we're going to do, we're going to simulate a hypothetical online algorithm on some initial access sequence, access the first K pages, then the cache is filled. And now we inductively proceed as follows. We consider, so let's suppose this is the current state of the cache in our hypothetical or simulated execution of the online algorithm A contains K different pages, right? Different pages It will never contain the same page twice in the cache. And since our main memory is larger than K, there exists a page which is not in the cache, and we will construct our bad input sequence now to just access that very page that is currently not in the cache. So the online algorithm is forced, we enforce it to evict the page in order to lay the new page. And then we repeat that. Now it's still K pages, maybe different ones, but K plus 1 pages in the main memory. So now we extend our sequence to access a very page that is not currently in the cache, and thus forcing the online algorithm to have another page fault, and so on. And you see that this can apply to any online algorithm, right? We can, as a user program, always create such a bad access pattern where our user program accesses just the page that is currently not in the cache, and therefore forcing the online algorithm to have a fault on every single request. Okay, but in order to prove the claim, we also have to show that an optimal offline algorithm can do much better than this, right? So we're kind of fooling the online algorithm. We're using our adversarial techniques. We use that we somehow know in advance what, or we can create the user program to access sequence artificially, right? The user program may not know how which online algorithm is running, but we know it, we analyze it, and we create this bad adversarial access sequence. And now let's compare that to an omniscient offline algorithm. And we've already used the pigeonhole principle previously, right? So the cache has size K, but the main memory is larger. So in each round, we can find a page which is currently not in the cache and force the sequence to access that. Here's another nice application of pigeonhole principle, namely the omniscient optimal offline algorithm, or we construct such an offline algorithm which behaves as follows. When presented with a cache miss, it looks at the next K pages being accessed. And this is only feasible for an omniscient algorithm, right? Only an omniscient algorithm, which K pages will be accessed next. So the current page is let's call that page number 1, has caused a cache miss, and we look at the next K pages, and so this makes a total of K minus 1 pages. So at least one of the pages in the current cache must be different from these K minus 1 pages, right? So currently in the cache, there are K pages, and in the next K minus 1 steps, the user program will access only K minus 1 pages. So at least one page in the cache will not be accessed in the next K steps of the user program. And this is a page that we will evict. Let me say that again. So our user program knows which pages our optimal offline algorithm knows which pages the user program will access in the next steps, in the next K steps. And these are only K minus 1 pages, because the page we're currently looking at is the one that has caused the page fault. So there are only K minus 1 different pages to be accessed by the user program, as opposed to K pages currently in the cache. So at least one page in the cache will not be accessed among the next K minus 1 pages accessed by the user program. This is a page which will not be used and therefore can safely be evicted, because it will not cause, evicting this page will not cause another page miss in the next K steps, in addition to the current page fault, so that the omniscient offline algorithm, by looking into the future can make sure that in this phase comprised of k excesses, only the current cache miss is suffered, and the next k-1 page excesses will not incur a cache miss, making a total of just one page fault compared to the arbitrary but fixed online algorithm for which the sequence we've just created, the worst case access sequence, it occurs k page faults in the next k accesses, namely it occurs a page fault on every request. So put differently, being able to look into the future allows the omniscient offline algorithm to make sure that a page fault is suffered only on every case request, whereas we've constructed the sequence so that the online algorithm will suffer a fault on every request. That means there's a factor of k between both. So that means on this bad input sequence, indeed, the arbitrary but fixed deterministic online algorithm will suffer k times more page faults than the omniscient offline algorithm. It is at least competitive ratio is at least k. This concludes our proof of optimality of the least recently used strategy. And I'd like to emphasize that this applies to deterministic online algorithms, because in the final slide, which unfortunately we won't be able to cover today, we will consider also a randomized online algorithm. That means we combine the two algorithm paradigms from the current and the previous chapter. So chapter 6 is about online algorithms and competitive analysis. Chapter 5, as you recall, was about randomized algorithms and expected case analysis. And we will here design a randomized algorithm for the ski rental problem. Remember, we proved that ski rental is optimal. Competitive ratio is 2 minus 1 over d. And here we will construct a randomized algorithm that beats that competitive ratio, has competitive ratio strictly less than 2. So that's all for today. Thanks for attending. Thanks for your interest.